the order of business for today, which is talking about prediction intervals and feature importances. So this code I just copied and pasted from last class, so we're not really going to go over it again, but I got my pipelines for each type of feature, got my column transformer to distribute those pre-processing pipelines over the different columns. I fit it, I get the names of the new columns, and this is kind of, I'm not really going to use this, but just in case we want to look at what the data set looks like after encoding, and we looked at this last time, we've got all that kind of encoded variables. Okay, here we go. Ensembling with regression. Yes, this was the thing we didn't have time for last class, so I moved it to the beginning of today. Okay, so a week ago we talked about ensembles and voting classifier and stacking classifier. So I want to point out a few things. We have these analogs in scikit-learn, voting regressor, stacking regressor. We also talked last Thursday about all these fancier trees, XGBoost classifier, and we have all those analogs as well. Just replace classifier with regressor and you're basically good to go. So we can do all the same stuff we did a week ago. We can take a whole bunch of regressors of different kinds, and we can, I'm getting the results for each one individually. And so we can see that apparently XGBoost and random forest are both getting around 0.82 r squared. And you can see the standard deviation. You can see how long it took. In this case, XGBoost took longer than random forest. And then you can average them together. So that's what voting regressor does. I can fit, I can get the score. Let's see if we do any better than either of these or not. We might or we might not. Oh, in this case, we actually do a bit better. So the best one before was 0.82, but when we average them, we get 0.84. Although, again, that could be random luck because the error bars are pretty big here. So we might want to use more folds. What I wanted to talk about is how the predictions are generated. So if I predict on the first test example, I predict $225,000. And if I look at each base model making these different predictions, and then I average these four numbers, I get exactly that same prediction as above. So the reason why I've been calling it averaging, with classification, it was really voting. But with regression, it's literally averaging. It's taking the four models, each one makes a prediction. It's literally taking the mean of these four to get its prediction. Yeah, so there's also stacking. If you recall, stacking was where you had this model on top of the input of this, the meta model was the output of the individual models. And so here, since it's regression, our meta model is by default linear regression. Whereas before with classification, our meta model was logistic regression, which is linear classification. So we can do all that same kind of stuff. And I'm just running it to see what the score is. Although again, the error bars on these scores are pretty big. So if I was willing to wait longer, I should probably use a lot more folds. Does linear regression have something analogous to predict proba? Did not pay you to ask that question, but thank you for asking it. That is one of the main two topics we're going to be talking about today. So hang on for that one. How big is too big for error bars? Well, I guess if I'm comparing 0.8 to 0.78 and I'm saying, oh, 0.8 is better, well, I shouldn't be saying that, like if the error bar is way bigger than that difference. So it's too big when the error bars is way bigger than the difference between the best one and the second best one, and you show up and confidently say, oh, this is the best one. Okay. So we can look at the coefficient. Yeah, I should wait for the designated question answer periods. I'm not following protocol, but this is the standard deviation of the test score across the folds. And there's only 5 folds here, and it would be more meaningful with, say, like 20 folds. Okay. Let's see. We can look at the coefficients, right? So the meta model Oh, this is fun. Okay, so the meta model is linear regression. These are the coefficients. So it seems to trust XGBoost the most, and it actually has a negative coefficient for decision tree, which is kind of hilarious. So the stacking learned to do the opposite of what the decision tree said. If decision tree outputs a higher prediction, the stacking model is actually going to output a lower prediction. I mean, that's just kind of noise, and as you can see, it's very close to zero, but it's kind of funny how little it thinks of the decision tree. The decision tree seems to think it's basically garbage. And so this is all very analogous to what we had in the lecture a week ago. And yeah, this kind of makes sense. The coefficients are bigger for XGBoost and random forests, which got higher scores. So the meta model is learning to trust random forest and XGBoost more and trust decision tree less. Yeah, so in classification, the stacking model took the output of predict proba to get its inputs. And as someone mentioned in the chat, we don't have predict proba for regression. And that's, so stacking is just using the output of predict. That's already a number, so that's fine. But the next thing we're going to talk about for the next 20 minutes is what is the analog of predict proba when we're doing regression. Okay, so now I'll do a question period since we reached the end of this section. Are we passing the target? No, so I wasn't doing any log transforming there in the demo. The coefficient is close to zero. Does it mean the model is pretty much disregarding the output of the decision tree? Exactly, because it's taking the output of the decision tree and multiplying it by a number close to zero. And so it's basically disregarding it. So it's a very interesting question about these coefficients being percentages. They actually don't have to add up to 1. It's just they will kind of tend to add up to 1 because all of these models are trying to predict the same thing. And so it's kind of taking a weighted average of them. And if these coefficients added up to 5, then the predictions of the stacking model would just generally be way larger than the individual predictions. And that doesn't really make sense. Like, the individual predictions should be doing reasonably well. So you don't want to, if they predict around 200,000, you don't want to be predicting like $1 million. So the coefficients will typically add up to something close to 1. And you can think of it as being close to a weighted average, but that's only coming from the data. It's not actually forcing the coefficients to add up to 1. It's just realized that was the right thing to do. Is stacking using logistic regression by default? For classification, it is, but this is regression and logistic regression is not applicable. So it's using ridge. If you look at, what is the thing called? Stacking regressor. Look at the documentation. It says that, where is it? Yeah, it's basically using a ridge. By default, but you can set it to whatever you want, just like we did with classification. Okay, moving on. Prediction intervals. So exactly this question. Can we get some notion of confidence or range when we make a prediction? Because if I predict a house price as 200,000 and my model says plus minus $1,000, then or plus minus $1 million, that's very different for me. In one case, I'm like, oh, the model's pretty confident. I should maybe believe it more. In the other case, the model's basically saying, I have no clue how much this house is worth. And so if the model could communicate that to us, that would be awesome. And so that's exactly what's happening here. So I just like massive amount of disclaimers for this section. This is a section I've added to the course this year. It wasn't in it last year, but I think it's really important, which is why I'm adding it. But it's also going to be like impossible to not upset the statisticians in the way we're going to treat this in the course. And so we're just kind of disregarding all of statistics here because we don't have time and because we don't have prereqs for this course in statistics. But there are all kinds of intervals you may have heard of, confidence intervals for parameters, for predictions, prediction intervals, kind of principled mathematical ways of getting to these things from mathematical statistical models. We're not doing any of that stuff. We're just going to use the term prediction interval very loosely to mean like a range of values, a plus minus, if you will. I predict the house price is 200,000 plus minus 50,000 or plus minus 10,000. And we're not really going to interpret it in any kind of rigorous way, kind of like with predict proba. We just thought of it as a score and not really as like a formal mathematical thing. We're going to do the same thing here. So there's a bunch of ways you might get prediction intervals. And again, if you have stats training, you might have heard of bootstrapping, which is not something we're going to go into here, although it relates to the way random forests work. Since we just talked about ensembling, what you could do, although I'm not really going to recommend it, is you could just look at these 4 predictions and say, well, the lowest one here is 222,000, and the highest one is 228,000. And so I guess I can just say my prediction interval is it's somewhere in between 222,000 and 228,000. And 225 is in the middle. So you could do that, but I don't really, or you could take the standard deviation of these. I don't really want us to do that as the default way, because you might have some crazy model in here doing weird stuff. And it's just kind of hard to interpret this. So yeah, I'm going to move past that into the main thing that I want to talk about, which is called quantile regression. And so quantile regression is essentially changing your error metric when you're doing regression. So we talked last time about error metrics like R-squared or mean squared error or MAPE. But all those things were kind of trying to get into the middle. Let me show you the picture and then we'll talk about the text. So remember we looked at this kind of picture last time where we had the true price versus the predicted price, which is this really nice diagnostic we can do in regression that was sort of like the analog of the confusion matrix-ish for, predicted, for regression. And what you can see here is that we're kind of along the middle here. We're kind of too big some of the time and too small some of the time. But we could change our error metric if we wanted. Like when we did MAPE, if you recall, sometimes we were off by, it was 10% too big, 4% too small, 7% too big. And we just took the absolute value of all those and said, you know what, let's just get the error. We don't care if it's too big or too small. We just want the mean absolute error. But what if you did care if you were too big or too small? What if you said, you know what, predicting the house price too high, that's going to totally mess me up. I never want to do that. If I'm going to be wrong, I'd like to be wrong by being too low. You can have an error metric like that that penalizes being too high much more than it penalizes being too low. And it's very analogous to what we did with classification with penalizing false positives versus false negatives and all that kind of stuff. So that's what quantile regression is, and we're not going to go into the math, but I'm going to show you some tools that already have that built in. And so I'm going to focus on the light GBM, which has that built into it. And so here's my light GBM, just regular default everything on the training set. And yeah, just first off, like this looks like it's pretty good. And here's what I'm going to do. I'm going to pass in the hyperparameter to light GBM saying objective equals quantile. So do this thing called quantile regression and set alpha equals 0.9. And what that's going to say is I want you to predict big so that I want my prediction to be too big 90% of the time and too small only 10% of the time. So I want to skew my predictions to be extra big. And this 0.9 means 90% of the time. My goal is that my predictions would be too big 90% of the time. Normally, you kind of expect 50-50, half the points on top of the line, too big, half below the line, too small. But let me skew things. And this comment here is saying just the alpha thing is like so horribly overused because this is called alpha for the quantile. It has nothing to do with the alpha in ridge, and sadly nothing to do with the alpha in plotting, which has to do with how transparent the points are. So within one screen, alpha is meaning 3 completely different things, which is very unfortunate, but I can't really change that. So just keep an eye out for that. So here's what I'm going to do. I'm going to fit the LGBM with this hyperparameters. And here's my scatter plot. And what you can see is that it tried to be, we basically told it, look, I really don't want to underpredict. If I have to be wrong, I'd like to be too big 90% of the time. And you can kind of see this in the results. Like almost all the errors now are that the thing is too big, and it's hardly ever predicting too small. So it's kind of giving you like a, well, yeah, it's kind of predicting on the high side for the house price. And it's unlikely to be too low. And the chance should only be 10%. That's, again, what this number is. It's a percentage, basically. So that's very cool. It did what we asked. It's, again, sort of related to this class weight stuff, and in that we're kind of fudging the predictions. And why are we doing this? Well, here's why. When we set it to 0.9, we got these two big predictions. And when we set it to 0.1, we got these two small predictions. And so now for every house in the data set, when we predict, let's use both of these. Let's make a prediction with our 90, our LGBM 90, which is going to give us a big prediction. Let's make another prediction with our LGBM 10. That's going to give us a small prediction. And then we can actually use that as our range, as our prediction interval. That's basically the punchline of what I'm getting at here. And then we can kind of say, well, we expect with 80% confidence. Again, we should be careful. As with predict proba, it's hard to take it too literally as a probability, but we can kind of say we expect most of the time the real answer will be in between the high prediction and the low prediction. Yeah, so this really changes things. Like this changes it way down here. There's some issues with outliers going on here that we'll talk about later, but let's do the prediction interval thing. So here's my first test example. This is the first property in the test set. We can predict with our regular LGBM, which use default hyperparameters, and we can predict with our give me a low value version, and we can predict with our give me a high value version. And we can say, you know what, I think the predictions, I think this house is worth between 213,000 and 224,000. What is weird here is that our original predict is not actually falling in between these two, which shouldn't happen that often, but unfortunately happened here. And without really going into the statistics of it here, this one is kind of like a mean, and these ones are kind of like quantiles. And instead of using the one with default hyperparameters for the middle, if we also use this quantile regression thing, but we do 0.5, that'll give us a better middle for this. So we'll not use the one with default hyperparameters for this. We'll do a 0.5 as our kind of middle prediction, and then a 10 and a 90 for our low and high predictions. And then we'll get the middle one is actually in between these two. This might, if we log transform the targets, actually this weirdness might not have happened. But yeah, worry about that later. Okay, so now we can make this plot, which is kind of the punchline here. So now for each prediction, we actually get these error bars, and they're not symmetric necessarily. You might have a lower bottom and a small, this part of the error bar might be bigger than this part of the error bar because they're just coming from three different models. But this is kind of cool because now every time you make, and notice the error bars are of different size. So this one over here, it was very uncertain. And this one over here, it was very certain. And what's really great is that when it was pretty confident, it was actually pretty close to being right. But look at how sometimes the true answer is not actually in the error bar. So in this case over here, you had this high and the low, but the true answer is still higher than the high. And so it's not going to always be right. It's maybe not even always going to be right a certain percent of the time. But it is nice to have these error bars. And it does give you a sense of that some predictions are maybe more confident or more believable than others. So let me pause for questions. Any questions? What if our values on the true values were also reported within some error bars? Yeah, I don't know offhand what to say about that, but it is true that sometimes you collect the data and you don't actually know. If you ask that on Piazza, I can look into it, but I don't have a good answer off the top of my head, and I don't think this is what you would want to use in that situation. How does it know to make 90% of the predictions high without knowing all the predictions? Well, I guess it does know all the predictions, at least in terms of the training set. So if I scroll back up here, I'm setting this up with this 0.1, and then I'm calling, oh, well, this is calling fit. It's not showing it here, but inside of here, it's calling fit. Just a minute. Where did it? Oh, I see. I'm calling fit over here. It's like, why am I not fitting? Yeah, so it is fitting on all the data at the same time with this information in mind. So it's going to try to do that 10% or that 90% within the whole training set that it has. But when we actually plot it on the test set, I mean, the test set is different. And so, yeah, this picture I showed you over here is actually on the test set. And so everything's a little different here. Okay, so yeah, you could also use something else like 0.75 instead of 0.25, and then you're going to get smaller intervals. So I'm just doing that here. You had these error bars over here, and if you do 0.25 and 0.75, you get kind of these smaller error bars. These look too small to me, but it's kind of up to you and what you're doing and what you want these intervals for. But I just wanted you to know about this. Because I think it is often very useful to have some notion of confidence or range when you make predictions. And in classification, it's built right into scikit-learn with predict-proba, and with regression, you have to do a little bit more work to get these out, and not all the regressors we've been looking at even have this, but some of them do. And I mean, there are some general approaches that would work for any regressor, but we're not going to go into those here. Any questions? Okay, 5-minute break. See you at 11:36. Don't forget to get out of your chair. Yeah, there's a question in the, there's a question about Ridge, and then I posted this issue in scikit-learn where people are asking to add quantile regression for linear regression, and it seems like there's a pull request that's in there. Anyways, another question, I find intervals hard to use when comparing models, like I have to see which model has smaller error bars. So you can always use the scores we talked about before to compare models. I wouldn't really use these intervals to compare models, because just like with predict-proba, you can change a hyperparameter C of logistic regression and get it to be more confident, and that's kind of meaningless. Here, you can always get the error bars to be bigger or smaller by using, you know, the 99 quantile or the 51 quantile. So you can kind of just make the error bars however big makes sense for your purpose, your application, your business reasons. And I would just use the regular score to compare models. And that's kind of, yeah, the one number. So like MAPE or dot score or whatever it is that you're using. Okay, next, feature importances. This is one of my favorite topics in the whole course. So hope we'll have fun with this. Logistic regression and linear regression both have these coefficients in them. And the prediction, in this case, the predicted price for a linear regression, is the sum of the the ith coefficient times the ith feature, coefficient 1 times feature 1 plus coefficient times 2 times feature 2. And there's also this intercept thing, which is kind of like the base price before you start looking at the features. Did we restart or not stop recording? I did restart recording. I was very careful about it this time. I heard the sound. I see the little red dot, so we should be good to go. Oh, can you not see me? Oh, okay, all good. Right, so I am going to make a linear regression model here and fit it on our training set. What I'm going to do now is I'm going to print out the coefficients. The reason I have this 1 here is because the LR Python object is a pipeline object. And if I grab 1, that's like the second element. The 0th element is the column transformer, and the 1 element is the ridge. That's why I have the 1 there. So LR1, and then I'm grabbing the coefficients, and then I'm just putting them in a pandas data frame for visualization purposes. And what we see here is the coefficient for each feature. And so we did talk about this with logistic regression, like if there's a positive coefficient, then that word means it's more likely to predict as a positive review, and so on and so forth. And it's the same kind of thing here. So this is positive. That means that higher lot area gives you higher predictions, and higher overall quality gives you higher predictions. That makes sense. Higher quality leads to higher price. This one makes sense. A higher year. So if it's a more recent house, it gives you a higher prediction. This one's a little funky, that the lot frontage, like how many feet there are at the front of the yard or whatever it is, gives you a negative coefficient. That's a little confusing, and we'll talk about that a little bit in a minute. A higher prediction means a higher predicted price. So it's predicting the price of the house. It's giving you a number. And if I change the overall quality of a house to be higher, then the price that it predicts for that house will be higher. Okay, so there's also this intercept thing. We're not really going to worry about that. Let's just not worry about it. Okay, so here's 2 coefficients that I'm going to focus on for a minute, the pool area and the lot frontage. And so increasing the pooled area by 1 scaled unit increases the predicted price by $6,400, and increasing the lot frontage by 1 scaled unit decreases, because of this negative sign, the predicted price by about $1,800. So does that seem reasonable? I just talked about that. Sure, a bigger pool, more price. Sure, I can get on board with that. Bigger frontage, smaller price. I'm not really sure. And in general, one of the main messages I want to get across today is we cannot draw causal conclusions here, meaning we cannot say, we don't have the statistical training in this course to make causal inferences, like if I go home and smash the ground and make my pool a little bit bigger by 1 square foot, then I'm going to be able to sell my house for an extra whatever $1,000. Like, we shouldn't make conclusions about the world that we live in. All we should really say is we can draw conclusions about how this particular machine learning model will make predictions. We can say for sure it is a fact that if I put the pool area bigger, this ridge model will give me a bigger prediction. That is true, but we don't want to take this and say things about the world without statistical training to do that, because you could be completely wrong, actually. So yeah, I would say this lot frontage thing is an example of that. I don't really buy that. I think having a bigger lot is probably a good thing. And so yeah, there's like, here's maybe what's happening here. So there's lot frontage, which is, I think, like the length of the front facing side. And then there's lot area. And lot area is basically lot frontage times lot depth. And so these 2 things are kind of similar to each other. And lot area has a positive coefficient. And so it may be, what if people like having big lots to sell? That makes sense. But for some reason, they like narrow lots. Then maybe they would give a really big coefficient to lot area and a negative coefficient to lot frontage, because if it was big but had a small frontage, then it would be very deep or something like that. So you have to be very careful about these kinds of conclusions about the world. And there's just so many things that could explain these patterns. Not to mention, if you change the hyperparameters, you could get completely different coefficients. And so it's just all very fragile. I just want you to feel that. Don't feel too confident about that these numbers are telling you something about the world. Here I'm drawing a correlation plot just to show that lot frontage and lot area, the higher colors, a higher number. So these two features are pretty correlated with each other. It means that in the X, when lot frontage is high, lot area tends to be high. And it's a higher correlation than, say, the area with the quality or all that kind of stuff. So these correlation plots can be useful to just see which features are correlated with which features are behaving similarly to which features. Let me stop for questions here. Is this the same thing as feature importance? Well, it is very related, because if the coefficient is very big, that feature is very important to this model. If the coefficient is 0, that means it's actually ignoring that feature because it's multiplying that feature by 0, and so it's not even looking at the value. So looking at the coefficient in linear regression tells you how important that feature is to that model. Correlation is not causation. Definitely agree with that. If we make a model based on individual variables, could we make better conclusions on the real world impact? Well, yes, but even then, not without more statistical training. Should an overall condition and year built have correlation? Good point. Yeah, so they're black. Black seems to have a negative correlation. So that means when the condition is higher, then the year built is lower, which is surprising. But it depends how these things are encoded. So if we really wanted to investigate this, we have to go back and see what type of feature is overall condition even, and how's it being encoded. So I'm going to scroll up for a minute. I won't spend too long on this, but I think it's a great point. Can someone find overall condition here? There. Okay, so I see. So this is actually a numeric feature. So now we would really need to open this text file and read about overall condition to even understand what this feature represents. Like, is higher better? Is lower better? I'm going to guess higher is better, but yeah, not sure. Okay, where was I? Yeah. Yeah, so with these things, we really need to dig into what these features mean. Okay, so here's what I'm going to do to kind of prove to you about this coefficient thing. I'm going to take a test example, in this case, the first test example. I'm going to use our linear regression model to predict on it, and it's predicting 222,000. So here's this test example. And then I'm going to do this perturbed thing where I'm going to make a copy of this row here. And I'm just going to increase the lot area by 1 manually. So I now have this exact same thing, except the lot area used to be 9505, and now it's 9506, and everything else is the same. And the prediction used to be 222,000. And I'm going to say, what is the prediction now? What if I predict on this exact same thing, but with 1 bigger square foot of lot area? And what I get here is a prediction that's larger by, what is that, 40 cents? Same number of dollars. It's about 40 cents higher when I increase the lot area by 1. And yeah, I subtract them, I get around 40 cents. And yet, I said the coefficient was 3,000. So what's happening here? I thought you got the prediction by multiplying the coefficient by the feature, And if that's true, and then if I increase the feature by 1, shouldn't the prediction be going up by $3,700? And yet it's only gone up by 40 cents. So what is going on here? Right. So someone has given a suggestion in the chat. So the issue here is the units and the scaling. So lot area was a numeric feature, which means that in our pipeline, it was getting scaled by standard scaler. And so the linear regression, the ridge, what's feeding into it? Well, what's feeding into it is the scaled features, not the original features. And so when we see this coefficient, what this means is that when you increase the scaled features by 1, then the prediction goes up by $3,700, not when I increase the original thing by 1 square foot, because what's feeding into the linear regression is these scaled features. So we have to be very careful about that. And so we're going to actually untangle this mess. So let's untangle the mess. Here's our pre-processing thing. I'm going to grab the numeric part of it, and I'm going to grab the standard scalar out of that pipeline. So this scalar object was the standard scalar that did stuff to our numeric variables. And what the standard scalar did, to remind you, is it subtracted off the mean of every column according to the training set and then divided by the standard deviation. So that dividing by the standard deviation changed the scale, changed the units of things. So 1 square foot was not the same as 1 unit after scaling. And I can print out these standard deviations. This is now 1 for each column. And I'll put it into a data frame so we can see it. So these were the scales. And I'm actually grabbing this out of the standard scalar object, which has this attribute that gives me the variance, and I'm square rooting it to get the standard deviation. So this is what got divided by. So originally, lot frontage had a standard deviation of 21, so we divided by 21. Now it has a standard deviation of 1. Originally, lot area had a standard deviation of 9,500, so we divided by 9,500 to make the standard deviation. We were just talking about lot area. Oh, well, switched it from lot. Oh, hey, my internet cut out there. Is it back now? Sorry about that. Okay, let me rewind myself by 30 seconds. Okay, this is the standard scalar object that I am pulling out of my pre-processing pipeline. And the standard scalar object subtracts the mean and divides by the standard deviation separately for each column. And so what I've done here is I have extracted the standard deviation. The standard scalar object has this variance attribute. And I'm square rooting variance to get standard deviation. And what we see here is the original standard deviation of each column before it was scaled. So the area is huge. That makes sense because you had lots that were 1,000 square feet. You had lots that were, I don't know, 50,000 square feet, multiple acres. And so there's a big standard deviation around 10,000 square feet. So we divided all the lot areas by this number, around 10,000 square feet, so that the new standard deviation would be 1, because that's what standard scalar does. Lot frontage, the original standard deviation wasn't that big. You're not going to have a million feet frontage facing the street. So here the numbers weren't as big originally, so we divided by 20 again, so that after scaling, the standard deviation was 1. So for each of these columns, all the numbers were divided by the numbers shown here to make the standard deviation 1 for each column. Are we still, am I still good? People still connected? Okay, thanks. And then I was surprised when I did it the first time, but now I'm just, for some reason I switched myself from lot area to pool area in the middle of this example. My bad about that. So yeah, it's just very annoying. Let me deal with the lot area because that's what we were just talking about. So lot area had the standard deviation of 9,576. Okay, so what we saw before was that the coefficient was around 3,000, but we also scaled it by around 9,000. And so if we divide these two, we get this unit conversion ratio that says, okay, actually, in the original units of square feet, if we increase the lot area by 1 square, so if we, okay, slow this down a bit. This was that coefficient we had. So if we increase the lot area by 1 scaled unit, the price went up $3,700. However, as it turns out, 1 scaled unit represents 9,000 square feet. So if I just want to know, well, what about 1 square foot? Then I need to divide this by this, which is what's happening down here. So this ratio tells us if I increase the original lot area by 1 square foot, then the predicted price should go up by this amount. And that's exactly what we saw earlier, that 40 cents. And so I'm just kind of recovering that result that we had earlier. And so basically, long story short, if we take the coefficients and we divide them by the scales, now we actually get the proper interpretation that we want, which is if I increase the original number in the original units, be it square feet or whatever, by 1, then this is how much the prediction goes by, 40 cents. So yeah. Did I print these out? Right. And this is all only for the numeric features. So for the one-hot encoded features, we don't have to worry about that because those were scaled. So the one-hot encoded features are only 0 or 1, and so we can just interpret them directly as if I have this category, then the price goes up this much. But for the numeric features specifically, we have to worry about that. Yeah, so the scale is kind of the original size. It's the original standard deviation of those values, which we then divided by before sending it into Ridge. Questions about this? I would say this is fairly not obvious. Isn't the coefficient the original size? The coefficient is a property of the linear regression, and the linear regression was taking in scaled values. And so all the coefficients of linear regression are getting multiplied by the scaled values. And so all those coefficients are with respect to scaled values. So if we want to increase the money by $3,700, we have to add $9,500 to lot area. Exactly, perfectly said. If we increase the lot area by this amount, that increases the scaled lot area by 1, and therefore increases the predicted price by $3,700. Is the scale the standard deviation of the coefficients? No, the scale is the standard deviation of the original data. So X train, the original data lot area, these things, the scale is the standard deviation of these things. And I can show you that. So we get that. Yeah, well, yeah, close enough. I don't know why it's very slightly off, but it's basically that. If I have to log the numeric data, would we have the same problem? Yeah, so we'll get to that in a couple minutes. The log adds yet another layer of confusion to what's happening here, but nothing we can't handle. It's just a lot to wrap our minds around. By the way, the ordinal features are something else that would be fun to talk about. Yeah, I don't really want to talk about inverse transform. Oh, good. Let's talk about this. This will be more fun. The categorical features. So we didn't scale the categorical features, so we don't have to worry about this. So here's our ordinal features like exterior quality, basement quality, fireplace quality. And so if I look at the coefficient for, say, exterior quality, then it's 5,941. But we never scaled exterior quality, so we don't have to worry about this. We can just say this coefficient is being multiplied by the exterior quality, which is an integer because we did that ordinal encoding. And so the ordinal encoding, there was like poor, fair, average, good, and excellent. And so if you increase by one category, like from good to excellent, then you increase by this many dollars. So these, excuse me, these ones are a lot more straightforward to interpret. And maybe I should have explained this in the other order with the easier ones first. But right, there's not really any funny business going on. Someone did ask a couple classes ago, like, should I scale after doing ordinal encoding? And I was kind of like, don't really bother about it. And since we didn't do that, we don't have to worry about scaling here. So apparently exterior quality is a big deal because just going up one category in that, you get an extra $6,000. Well, that kind of makes sense. I mean, it is important to have good quality. The one-hot encoding features have their own joys. So here's our one-hot encoding features. Here's their coefficients for the land slope one. So land slope had three categories: gentle, moderate, and severe slope. And each of the categories became a column, and then that went into linear regression. And so each of the categories got its own personal coefficient because it was a column, and each column gets a coefficient. So therefore, each of the three possible values of land slope got its own coefficient. And it's a little hard to interpret these, but basically what we really want to think about is the differences between them. So I guess the zero part would be like if you were in an unknown category of land slope, that would be kind of zero. But what I'm doing here is I'm taking all these and I'm subtracting off the coefficient for gentle land slope so that gentle is zero, just so we can see. So this number is the difference between gentle and moderate, and this number is the difference between gentle and severe. And so what we can see here is that if you changed your slope of your property from gentle to moderate, then the predicted price would go up by $13,000. If you change the slope of your property from gentle to severe, then the price would go up by, predicted price would go up by $5,800, which I actually find pretty surprising because I would have thought gentle slope would be the best and severe would be the worst. But according to this, moderate slope gives the highest prediction and gentle slope gives the worst prediction, and severe is in between, which I find pretty surprising. And again, that's probably not how real life works, but this particular model and this particular small data set decided to learn this information. And so we shouldn't take it to be a conclusion about the world, but this is what it decided to do here. So apparently in this data set, having a moderate slope gives you the highest prediction. I don't really want that. Yeah, there's some stuff about drop first, but these days I'm just saying don't do drop first with one hot encoding, so we don't really have to worry about that. Okay. Actually, any questions about the one hot encoding thing before we move on? If this was a real world problem, how would you handle the situation like when the coefficients contradict common sense? Good question. This is an interesting question. If you only care about your model being good at predicting, then you can just say, you know what, I don't care. I'm just going to do my good random search CV, whatever, cross-validation. I'm just going to get the best thing that predicts. And if you trust everything, then you can just let it do that. And maybe there's a good reason to do that. And maybe it's right and you're wrong. Who knows? But it kind of depends on what industry you're in and why you're doing this. Like if you're in the finance industry and it's like heavily regulated and it really needs to like be interpreted why the model is making this prediction, maybe you would care more about that and you would try to do something about that. So it depends what you're doing, whether or not you care about this. And if you do care, I guess I haven't really thought about a suggestion for how to force it to think that way. So I would have to think about it later and get back to you. Any other questions about these coefficients? So we talked about how to interpret the coefficients for the numeric variables, which was kind of the messiest, and then for the ordinal variables, which was maybe the simplest, and then for the one-hot encoding, which was reasonably okay as well, but we kind of had to think about going from one category to another. Okay, so here I've sorted the coefficients, and here we have some very big coefficients. Apparently, if your roof material is clay or tile, your predicted price will be $176,000 left, which is pretty insane. And yeah, if you made alpha bigger, then this coefficient would be smaller, but I just use the default hyperparameter. So yeah, I wonder if there's still some randomness in here that I haven't dealt with. Anyways, these are the coefficients. And so here are the roof material coefficients. So yeah, basically clay and tile is giving you a really low price and everything else is better. And I guess the best roof material for predicting a high price seems to be wood shingles. But yeah, who knows if that's because wood shingles are good or because houses that have wood shingles tend to have other desirable properties as well, especially on this small data set. So I'm just saying over and over and over again, don't draw conclusions about the world because I don't want you to. Okay, someone asked about log space. Let's talk about log space. So here's my log transformed y values. Here's my coefficients for lot area and lot frontage. So we keep the intuition about the sign. The fact that this is positive still means if I increase lot area, the predicted price will go up. And this negative still means if I increase lot frontage, the predicted price will go down. But if we increase lot area by 1 scaled unit, then we increase the log predicted price by 0.013 because that's what we're doing here. We're predicting the log price. And so what does it mean to increase the log of something by 0.013? Well, the new logged price is the old log price plus 0.013. That's what we're doing here. And if we take the x of both sides, which is the inverse of log, then the x of addition becomes multiplication. And so what we see here is that the new prediction is the old prediction times some factor, actually times x of 0.013 by 1 scaled unit. So if we take the exp of the coefficients, here's what we get. Exp of 0.013 is apparently this. And so what this means is that before our intuition was we increase lot area by x and we increase the price by y. Now it's we increase the lot area by a certain amount and we multiply the predicted price by a certain amount, which is the same as saying we increase it by a certain percent. So 1.013 is basically 1.3% bigger. So every time we increase the lot area by however many square feet that was, 10,000 square feet, the predicted price goes up 1.3%. Number of bedrooms is an integer variable. Every time we add a bedroom, the predicted price goes up by 3% or whatever, I didn't check. And that makes so much sense intuitively. And I think it's another reason, another argument for why log transforming makes so much sense here. Because yeah, adding another bedroom or adding more quality of the roof, that probably intuitively increases the value by a certain percent. It doesn't make sense to say it increases the value of by $6,000 because for a giant mansion, having an awesome roof probably increases the value by more than $6,000. $6,000 is too small compared to the price of the giant mansion. But increasing it by 1% when you upgrade your roof or your number of bedrooms or whatever, that actually makes sense. And that's exactly what log transforming combined with the linear regression is doing. So that's pretty cool, I think. And likewise for the negative coefficient, exp of a negative number gives you something less than 1. And so here, when we increase the lot frontage by 1 scaled unit, we multiply the predicted price by 0.998, or in other words, it goes down by 2%. Questions about that? Okay, I'm going to plow full speed ahead because there's some stuff on here that I want to get to for your homework. So this is just kind of doing some experiments to verify. It's doing the same kind of perturbation thing as before and just verifying that what it says would happen actually happens. So it's increasing the lot area by 1 scaled unit, and then you can see the price actually goes up by 1.3% like it's supposed to. Okay, gosh, we gotta, silly me and my time estimates. Okay, I want to talk about this idea beyond just linear models. Linear models, which for our purposes means logistic regression and linear regression, have these coefficients, which is awesome. And so they're kind of the super interpretable models that you can just really understand what they're doing. But some other stuff like light GBM or random forest, it's not so easy for us to understand what they're doing. And so I'm going to talk about two things. And by the way, I'm kind of, for the purpose of this class, restricting our definition of interpretability to just be feature importances, or what happens if we change a feature. Maybe there's broader definitions of an interpretation of a model, but we're not going into that. So here's my random forest. I decided to train on the log data. And random forest doesn't have a coef, it doesn't have coefficients, but it has something else. Feature underscore importances underscore. And it's still telling us it's still telling us how important each feature is. But they no longer have a sign. They no longer have a sign. Like with the coefficients for linear regression, one thing was positive means more of that means higher price. One thing was negative means more of that means lower price. This feature importance is just how important is it in an absolute sense. And so it's not giving us as much information. And why can they not give us a sign? Well, random forests are not linear models, which means as you increase the number of bedrooms, maybe the price goes up. And as you increase the number of bedrooms more, maybe the price goes down. A random forest can model that type of relationship, whereas linear regression can't. Linear regression can only learn that more bedrooms is good, or more bedrooms is bad, or more bedrooms is really good. But something like random forest can learn any kind of relationship, like maybe the best number of bedrooms is 3 or something. And so it wouldn't make sense to have the sign be positive or negative, because increasing a feature might make it go up and then go down. And so we only get this measure of importance here. And apparently the overall quality of the house is the most important thing, which is not super shocker. Because yeah, overall quality is something you want to have. So here's the ridge coefficients. Let me zoom out so we can see them at the same time, and then I'll zoom back in. So here's the random forest importances. Here's the ridge coefficients. Here the units actually mean something, like we just talked about. We can do with the scaling, we can interpret them. Here, these importances, I think they just add up to 1, if I remember correctly. So the actual numbers themselves don't really mean anything. So the fact that this is 0.54 and this is 0.01, 0.08 doesn't really matter. But you can see the order is pretty similar, which is kind of reassuring. Both random forest and linear regression agree that overall qual is the most important. And then they disagree on the exact order, but they both think garage is important and living area is important. For this one, by the way, I'm taking the absolute value of the coefficients for the linear regression, because I'm saying I don't care if it's positive or negative. I just want to know which coefficients are biggest, because that's kind of a notion of importance. And I know I'm going at high speed here, but I'll have to just keep going. Okay, so both models agree that overall quality is important. That makes sense. We should not compare the numbers. We talked about that. So this tells us all this stuff we've done for the last 20 minutes tells us globally which features are important. But it's a general thing for the whole trained model, trained on the whole training set. But what if we want to explain a specific prediction? What if we want to say, for this test example in the test set, why did this prediction get the particular price? That's kind of like the next level of interpretability. So which features in this case contributed? And that's what SHAP is going to do. So SHAP is this fancy thing. It came out in the last 5 years, I believe. I guess we can check the date on the paper. 2017, so pretty new. And you should have it installed when you installed the course environment. And what I'm going to do, we're not going to go into how it works, but we're going to go into how to interpret the output of SHAP. And so I'm going to try to make this tree explainer to explain our random forest. And I'm going to compute these things called the SHAP values. And this takes a couple of minutes to run, but it's basically what's different about this SHAP value thing versus what we've done before. Instead of computing a feature importance for every feature, it's computing a feature importance for every feature for every example. So instead of just giving us 292 importances because we have 292 columns, it's actually going to give us the whole thing, the same size as the data set, 1095 by 292, so that we can look for a particular example and investigate the feature importances there. So we can see the size of the SHAP values is the same as the size of our transformed data set. And now we can start looking at some of these cool plots. So this plot here, I took a particular training example. I said for training example 0, the prediction in log space is 11.9. Why did you predict 11.95 for this particular house? And now it can tell you, it can say, well, the base value is 12. And again, this is in log space. So 12 is kind of like the average house value. But you know what? Your overall quality was less than 0. And again, these are the transforms features. So less than 0 meaning less than the average overall quality. So that pushed you down. That pushed you to the left. And your ground living area was actually below average as well. So that pushed you down as well. But your basement square footage was actually pretty good. And so that pushed you up. And your lot area was pretty good, and that pushed you up. And all these factors combining, and each one pushing in a certain direction, a certain amount, overall, we got 11.95 as the prediction. And so for that particular house, you can kind of see, well, why is this predicted to be worse than the average house? Mainly because of its overall quality, but it did have some redeeming aspects like its basement. And so this is just so cool. You can really see what's going on. And you'll do that on your homework as well. And SHAP has a whole bunch of different types of plots. And you can play around with this after. I don't have time to show you, to go through all the plots at this exact moment. This is the one I want to focus on more than anything else. So what this is doing is it's going for each feature, and each dot on this plot is an example in the training set. And red means the feature value is high, the transformed feature value, and blue means it's low. And the x-axis here is basically the they call it the SHAP value, but it's basically like how much is this changing the prediction. So if it's positive, it's predicting a higher price. If it's lower, it's predicting a lower price. So for example, here you can see overall quality is higher, more red color is giving you higher predictions, and overall quality lower is giving you lower predictions. But if we look at like this feature, for example, garage type detached, we have the red stuff on the left and the blue stuff on the right, meaning that when this looks like a categorical feature. So when this is on, red, I'm actually predicting lower, and when it's off, I'm predicting higher. So actually, apparently, detached garages are bad. And this also shows how important the feature is, because look, this overall quality is really having a big effect on the predicted price. And these other ones are having smaller effects. Do I have time for this one? So this one's showing just for a particular feature, the ground floor living area or above grade living area. And again, each dot is an example in the training set. So SHAP automatically picks a color based on another feature, which is kind of, let's ignore the color for a minute. Basically, this says higher ground floor living area, and it's scaled. That's why it can be negative or positive. Higher living area gives you higher predicted price, but it's not just linear. And you can imagine all kinds of relationships here, like I was saying before. Maybe it goes up and it goes back down here. And indeed, here, this like massive house over here, apparently that's not so good. And maybe this is like the optimal size. And because, again, this is a random forest. With linear regression, you can only go one way. Bigger house is better or bigger house is worse. That's all a linear model can learn. But this random forest can learn these really cool kind of curvy patterns, and SHAP allows you to really explore it. And I'm doing this for the training set, but you can also do these SHAP plots on the test set to understand why, or even in deployment, when you deploy it, you can use this to say, why did it make a prediction? Is it important to use all the data to generate the SHAP values, or can you use a subset to look at some general trends? Yeah, it is not uncommon to use a subset because SHAP is just very slow. So that's actually kind of a normal thing to do, is just take like a random 10% of the data or something. Yeah, so there's some other tools similar to SHAP that you can look at as well. And I just find all this stuff really cool. And we'll talk a bit more about these maybe a bit later in the course, but you'll use SHAP at least a little bit in your homework. And yeah, this thing is actually called Explain Like I'm 5, because it's like explaining the model, interpreting the model. And 1 minute left. Yeah, so why do we want this information? We'd like to know if features are useful. We'll talk more about that next week. We might want to know what data to collect, like if I'm collecting more data, but it's really a lot of work for me to climb on the roof and check the roof type. And if I know the roof type's not important, maybe I won't bother when I collect more data. I can understand how the model is working. Maybe I have regulatory requirements. Maybe this helps me debug. We'll talk about ethics and fairness a bit later. So that I love these tools that help us understand. And yes, you can use them for classification as well, not just regression. So that's it, we're out of time. I'll post these questions on Piazza. Have fun with the homework on the New York Airbnb data. And I will see you next week.